We've been talking about time response. Okay, this is the chapter, and last class we discussed about performance parameters. For first order system. Okay, so here we looked at time constant. Right? We looked at rise time, and we looked at settling time. Okay, we'll start looking at second order systems. Okay. Again, even in the second order system, we are going to look at something similar. We are going to look at rise time, settling time, peak time, and overshoot. Okay, these are the performance parameters we are going to look for when we are going to discuss the second order systems. What we'll do is we'll try to understand what a second order system is. So if you look at a general second order system is given by B over AS square plus BS plus C. Okay. So here we have talked about this. I'm just going to remind you. Order of system is equal to number of poles of the transfer function. Okay. So here there are, or this is also equal to order of the denominator polynomial So this is a second order polynomial in the denominator, and that's the reason you get order of the system is 2. Okay, and this has 2 poles. All right. There are 4 types of second order system. Okay. And this is based on the based on the types of roots of denominator polynomial, right? If you have a quadratic equation or a polynomial of second order, you can expect one of these roots of denominator polynomial real and distinct. These are the options. Okay. Roots of denominator polynomial are real and repeated. Roots of denominator polynomial are complex. And the last one is imaginary. Okay, so we'll take a look at an example and we'll look at it in the context of the example. So can you see this as a second order system? Why so?
2, power 2.
Power 2, right? So if you correlate the denominator power 2, what kind of roots are those? It's a quadratic equation, right? So your S roots would be okay. these are the roots. Essentially, if you use the quadratic formula for finding roots, minus b plus or minus b square minus square root of b square minus 4ac over 2a. If you use that, you're going to get these roots. Alright? And what's interesting is if you do a if this input if this input is 1 over s, okay, what would the output be? 1 over s is what kind of input?
Unit step.
Unit step, right? So the output would be unit step response or the unit step output, right? If this is the output or response is the same, okay? So if you do a plot of a unit step response plot, okay, you're going to get the plot like this. Okay. And you can say that this is 1. Okay, this value is 1. Plot will look like that. Keep in mind your C of t. How will C of t look? A plus b e to the power of minus
A2.
right here. It will look, if you split this open, right, C of s over R of s is what? 9 over s square plus 9s plus 9, right? Which implies C of s is, if this is 1 over s, C of s is 9 over s into s square plus 9s plus 9. Right? And you can split this like this. A over s plus b over s plus 7.854, right? C over s plus 1.1. Okay.
Dr. Sen, you got CS over RS. What do you have going to the arrow of RS?
1 over s.
Okay.
Unit step input. Okay. So now C of t would be what? A plus b e to the power of minus 7.854 t plus c e to the power of minus 1.146 t. Okay. Of course, A, B, C will have their own values if you do the partial fraction expansion and complete it. And what you have done, what I have done here is, you can see that this plot is essentially you input values for t. Start from 0, 1, 2, 3, 4, whatever you want. And then what is the corresponding output of that? That is plotted here, and it will look like that. Okay. The second one look at this, 9 over s square plus 6s plus 9. So here, tell me what is S1? This is also a second order system, right?
Be -3.
Right. -3. And S2 would be?
-3.
-3. Alright. So here what is roots are? The second condition. Roots are real and repeated, right? Okay. So here if you plot this, I have to make this a little bit more dramatic and show you that it will look it'll gradually get there, okay? And I'll give you an example to explain to you what that means. The ultimate goal is for this thing is to get to 1. Okay? So it will gradually get there. It will take infinite amount of time, but it will get there. All right. In here, again, here as well, you're going to see that the ultimate goal is to get to this 1. Okay. This one will look more like it'll get there much faster. All right.
Carson, how'd you get the -7.854? Well, S1 and S2 for the first one again?
Remember this? You have S12 is equal to -b plus or minus square root of b square minus 4ac divided by 2a, right?
Yeah. Oh, that's what you used.
Yeah. So this is how you find the roots, right? So you apply this to so here your a is 1, b is 9, c is 9. Substitute that, you'll get one of them as -7.85. Okay, again here too you can go this route here as well, but it's easily factorizable, so we don't worry about it. Now here, tell me how would C of t look? C of t would look like a plus b e to the power of minus t, right? Plus Ct e to the power of minus t minus 3t. Okay. The third one So I want to just write this. This is the unit step response plot. Okay. Whatever you're seeing. And similarly, this is also unit step response plot. All these are unit step response plot. Because it's a unit step response because R of S is unit step input. So here, if you look at it here, what are the roots? The roots are I'm going to use this notation. Okay. This is again C of t. And this is t. Again, this is also unit step plot. Okay. And we'll end with this last one. We'll do a discussion.
Will R of S always be 1 over S?
It will not always be, but we are analyzing the system for a unit step input. It's one of the easiest responses to analyze. Okay, the RFS could be unit step, it could be unit ramp, it could be, for example, all these are very representative of what happens in real life. Okay, and I'll talk about that. Before, let's just finish this. Fourth one.
It says unit step response, right?
Yes, it does.
Thank you.
So here the roots are, anybody? What the roots are here?
Imaginary.
Right, it is.
Be at plus and minus 3.
No.
Oh, because one of them's imaginary.
Both of them are imaginary.
Oh, that's
You're not imagining, man.
quite right.
They don't exist in, always remember, complex imaginary always exist in,
Different dimension.
huh?
Different dimension.
They exist in pairs. The roots, if the roots are complex or imaginary, if it's a, can you have a complex root if it's if it's a first order system? It'll be just real always,
Real.
right? So it has to be at least a second order system to have complex or imaginary roots. Okay, and they'll always exist in pairs. You see, what are the pair here? The pair is -1 plus j root 8 -1 minus root j.
And you're using a J like an R. Using
Yes,
J
yes.
like
J is essentially, what is j?
a -1.
No, j square is
-1.
negative. And j is root of negative.
So why are you using J instead of R?
It's textbook uses that. So
Textbook.
Time to start breaking the rules. Use your own letters, Dr. Cindy. It could be a K for all we care.
Anthony does not play by the rules.
No, I don't.
You better be careful, Doris. He doesn't play by the rules, okay?
He doesn't care about the friction
Huh?
coefficient.
He doesn't care about the friction coefficient.
Yeah, because it said K.
And then just because you don't care, it does not mean it does not exist, okay? You should not be so... Of course, you don't have to care the rules, but you cannot ignore physics.
No. You don't need to put what the book in mind.
Physics exists whether you care for it or not.
See, Taurus, now you make him think that I don't think that physics is real.
He doesn't. Like,
Oh my god.
He doesn't think physics is real?
Yeah, he needs to after.
The earth is flat too.
That's close.
Okay, so here the system is going to look something like this.
Sine wave?
It's a oscillating response, okay? Again, this is T and this is C of T. Right. I'm also going to do this.
So would the top of the oscillation, would that be 1?
This would be 1.
Okay.
Okay.
He's something else, man. Hey, that's assignment's individual. You know that? Did you do the balance assignment?
Hmm?
You did the balance assignment? It's individual. The DBF thing? The pre-flight checklist?
Hmm.
It's on balance. It's in the general group, man. And Dr. Grell posted it in our Team 1 channel. I haven't watched it out.
All right, so take a look at this, okay?
This one.
Let's have a discussion. So now you understand what a second order system is, right? Second order system is defined by the polynomial in the denominator of the transfer function, okay? This is the transfer function, all right? The polynomial is this, and if the polynomial is of order 2, the system is second order, all right? If it's a second order system, you essentially, the roots can be 4 types, right? 4 options. It is nothing else other than these. The roots are either real and distinct. Before I get into this, if the roots, what is the condition for system to be stable? Do you observe something here? There's a big condition, okay?
That one looks stable.
Look at this plot, okay? The roots have to be on the left half plane, in that they are either, the roots have to be negative. We talked about this, right? Roots negative means this has to be a exponentially decaying, not increasing. If it is increasing, it is unstable. Okay? We don't talk about control if it's an unstable system. An unstable system is not controllable. So you have to always talk about systems which is stable and controllable. Only when the roots are negative. You see, all the roots are negative here. Negative, right?
So they all stay.
Negative, negative, right? -1. The real aspect is here. This is called a marginally stable system. This corresponds to this. Okay, it is not neither negative nor positive. It's so on the left half plane. This is called the complex plane. Sigma and j omega. All right. This is the real axis. This is the imaginary axis. All right. So as long as you establish that the roots are negative, you establish that the system is stable. Okay. When we talk about controls, we only talk about control is only for stable systems. Unstable systems cannot be controlled. All right. So we looked at stable systems. Now we look at what are the different types of stable systems. The roots can be real and distinct. If they are real and distinct, the system is called a, and I'm going to mark it in red. If the roots are real and distinct, the system is called a overdamped system. Okay. If the system are real and repeated, the system is called, I'm going to write here, critically damped. You understand? If the system roots are complex, it is called a undamped system. And if the roots are complex, the system is an undamped system. If the roots are imaginary, it is underdamped. Okay, roots are complex, it is underdamped. And roots are imaginary, it is called a undamped or marginally stable system. Okay, these words are very, very crucial. We'll use these words quite a bit. Real and distinct, overdamped. What do you understand by this? Think about it. Okay, if your aircraft is supposed to hit the ceiling, this altitude, okay, that is the target. How is this system getting there?
Smoothly.
It's gradually getting there, right? What kind of aircraft would do this?
747.
A civilian aircraft.
Yeah.
You got it? This is almost a perfect system in that it's getting there right and then stabilizing. It'll go there and then go back.
That looks rough.
Right. So this one, it does this and then stable. You understand? So what kind of system, what kind of aircraft would this be?
The regular small aircraft?
The fighter aircraft.
Yeah.
You got it? So they don't care, right? They will just go there. They have to. So this slope is very steep for fighter aircraft. This is kind of this. So it will gradually. What kind of runway do you need for this?
What kind of runway?
You
You need a long runway.
need a long runway for this.
Well, for that one.
You need a shorter runway. You see, it'll take off pretty. It'll not do that, right?
Yeah. It'll take off.
It'll take off. You can get away with a shorter runway for this. Anthony, what kind of runway is this? Give me an example.
He's gonna say.
Carrier. Aircraft.
Well, reason,
Aircraft
what
carrier.
I was saying, like when.
Got it? Can you do an aircraft carrier for this?
No. But sometimes they take up 4,000 or 5,000 feet just with their bombs and stuff, though. But that's a different situation.
But I try to understand some comparison, okay? This is a very perfect system. It is very difficult to achieve this system. But here you'll get optimum performance on both sides. You understand? This is a civilian aircraft. This is a
Military aircraft.
military aircraft.
No, it's Cessna can take off shorter distance.
Right. So this is somewhere in between. Okay, this critically damped. You understand?
Yeah.
It's somewhere in between. Now this system,
It's an RC plane. Sucks.
it'll never get there. It'll just keep doing this.
It's Tony.
That's how I like to fly my RC plane.
Okay.
Usually.
So this is an undamped or a marginally stable system. You'll never get to the desired altitude. It'll just keep on this thing. Okay. So here another example of this is you have seen these. Look at this word damped. Okay. You've seen these doors, right? Those automatically closing doors.
Mm-hmm.
So if you just, there's no control here now, okay? It's all just dynamic systems. You've seen those dampers, right? There are dampers which when you open the door, it will gradually close. You understand? It is supposed to close, it will gradually close. Here, it will go back and forth and close.
That's like the kitchen door. You have kitchen double doors.
Right, it will go back and door and then close.
Yeah.
Okay, it will go beyond what it is supposed to go. And it will come down, go back, go, and then this will perfectly close. Okay.
So it's like that one would be like the doors with the pistons on them.
Those are the dampers.
Yeah, but that would be like the critical.
All of them have dampers. Damped.
Yeah.
This one doesn't have a damper. Undamped. No damper. No piston.
That's
the
a
door.
broken
The
door.
door never closes.
It never closes.
That's a broken door. That's a broken door.
So it's like a revolving door.
It never closes. So you have to understand this in the context of. Give me an example for this.
The door is broken. off the hinges. It would never close.
A revolving door?
You've seen those balls doing this?
Like a pendulum.
Pendulum which will hit the ball and then one will hit and it'll keep going on and on and on. Have you seen those?
Oh, the ball.
Yeah.
Yeah.
A what?
You know the balls.
What's the
where
name of
you
that?
hit
That was the
one
name of
and it
that
hits the other
called. We
balls
did it.
and it goes.
What's it called?
Oh,
No.
the Newton,
Yeah.
I know what you're talking about.
Systems like these
get back
are
from your lesson, watch.
perpetual motion systems. Okay. They will. So if you look at Newton's first law, what does the first law say?
Object at motion.
Just stays in motion.
So only if it's an undamped system will it stay in motion. Why don't objects in motion stay in motion on ground?
Because of gravity.
And friction.
Resistance. There is a lot of resistance, right,
Yeah. With the air.
with air. If you look at an orbiting satellite, once you put it, if there is no moon has been put there and it is going on and on and on, right? It's undamped. There is no, the gravity is pulling it, but at the same time there is velocity which is just doing that. It's an undamped system. If you put a low Earth orbit satellite, it will be a damped system. It will eventually come down, right? There is some atmosphere there. So the atmosphere will create an external force and it will pull it down. Okay? So you understand these things?
Mm-hmm.
Okay, these are the dynamic systems. Okay, and I need you to understand these plots. These are called. This will be part of your exam, which
Should be before.
Just had exam, Dr. Sunday.
Mhm.
Just had exam.
These are called pole zero plots.
Oh, yeah. I remember those.
Okay, this will be a big part of your midterm,
When's
and
the next
midterm will
exam?
be
Next week's.
It's before spring break.
before spring.
Let's have it Tuesday.
I mean, after spring break.
You had one chance, you blew it up.
Take home midterm?
Huh?
Take home midterm? I think that's a good idea.
You do a midterm and you take home
your grade.
peace.
They can have peace.
Like, can we take it home over spring break and then return to you the following Monday?
You have to set at least some realistic expectations from me. Do you think I'll do that?
Can we get
Yes.
our midterm and our final and we'll just turn them into you at the end of the semester?
I heard that last semester you gave some take-home tests for this class.
See, the thing is, I'm trying to get you guys to get everybody to pass, okay?
Yeah.
And last time what happened was,
It's a small class.
It's
it
a
was a
small
small
class.
class and plus they had taken the course once, most of
Wait.
them.
Right.
You don't want to just keep getting them back to taking the course, right? To give some leeway. You guys are not taking the course the second time.
No way, man.
Alright?
Yeah.
But you guys can do better than you don't need to take home.
I guess you'll see after you grade our test, huh?
You're like, dang, these kids are going to get a few take-homes.
Anthony is going to sit beside you all the time.
Yeah.
No, today's just a special occasion. I wanted to be closer to you, doctors. Tori's had nothing to do with it.
Alright, any questions on these? So next class what we'll do is we'll look at performance parameters, but please understand these systems, okay? The correlation and what they are called, over-damped, critically damped, under-damped, okay? And these are in the context of, and these systems are, the classification is independent of the input, alright? Because the roots are independent of the input, right? The plot will show that, yes, they are an over-damped system, but any plot, even if you do a unit ramp response plot, it will look something like this. It will show that the system is an over-damped or a critically damped or a damped system. Okay. Any questions so far?
No, sir.
You're good? Just make sure you give your attendance.
When's our